Hi, my name is Nur Suryani Fairuz binti Muhammad Fauzi, and this is my group members Nur Alia Sarah binti Muhammad Yusuf, Nur Fatin Adelina binti Nordin, Nur Erina Alisha binti Rizwan, and Alia Natasha binti Muhammad Nur.
So we go to the introduction first. This task is carried out to fulfill the objectives of the assignment, which are as listed below. In the task, we mainly focus on the application of first-order differential equation, the total population in Angola, in the 2000 to 2020. At the end of 2020, the population in Angola is 33,451,132. In 1798, Thomas Malthus, an English clergyman, scholar, and economist, developed a fundamental concept for modeling and analyzing the human population. The implementation of the Malthusian model used in Task 1 is to find the growth of population in Angola. The Malthusian model assumes that the rate at which total population in China increases at a given time is proportional to the number of population at that time. The Malthusian model can be written as dp over dt equals to kp.
Next, we move on to the task 1, which is growth population in Angola. So this is our table for the population in Angola, and our data was obtained from the Data World Banks, where we observed the number of populations from the year 2000 to 2020. And next, we move on to the calculation to find our particular solution, where we apply the Malthusian equation, where k is the constant of proportionality. And then we continue using the differential equation method, where we separate the variables p and t, and then we integrate both sides of the equation. And we can also find the general solution by using T0, which is the year 2000. And we can come up with a general solution that become P equals to 16194869 e to the power of kt. And then we find the value of constant k by using the next year, which is 2000. And then we're able to come up with a particular solution, which is pt equals to 16194869 e to the power of 0.0335 t.
We plot our graph, which are graph of data set. At first, when we plot actual population from 2000 until 2020, due to that we can get exponential curve. Next, for graph of particular solution, we can see the differences value between actual population and particular solution. The dotted point is represent to actual value and the exponential curve is. After that, we calculate the future value in 2023 that t equals to 23. We just substitute t value into a general solution. Then it same goes to the past value in 1995, which is t equals to -5. We just substitute the value and we can get the value of population. In our discussion, we answer the given question. First, are the values calculated from the particular solution accurate with the actual values? And the answer is no. Second, find the percentage error. For the then we can get the value of percentage error for the past value, which is 0.0185%, and percentage error for future value, which is 4.7763.
So question 3, if there is any difference between the actual value and the value calculated from the particular solution, why do you think it is so? So I think this is because there are some reasons that might affect the accuracy, which are limited data availability, infrastructure limitations, and environmental or regional variability. For limited data availability, Angola might lack high resolution or updated data in areas such as demographics, infrastructure, health, or economics. So second, infrastructure limitations. Poor communication, technology access, and measurement tools can lead to gaps between actual condition and model outcomes. And lastly, environmental or regional variability. Angola's diverse geography may cause models to generalize too much. Question 4. What has affected the population growth in the past? So, Angola's population growth before 2000 was mainly affected by the Civil War, which is from 1975 to 2002, and poor healthcare. The war caused high death rates, disrupted healthcare and services, and reduced birth rates in unstable areas. At the same time, limited access to clinics and high infant and maternal mortality. At the same time, limited access to clinics and high infant and maternal mortality rates also slow population growth. Diseases like malaria and cholera make the situation worse. Last question, what do you think might affect the population in future? In the future, Angola's high fertility rate may continue to drive population growth, though it is slowly declining. However, long-term growth could be affected by ongoing health issues and a possible rise in mortality from diseases. If healthcare improves and birth rates gradually fall, the growth rates may slow over time.
In conclusion, our Task 1 goal has been successfully conducted, and we comprehend completely the application of first-order differential equations to our project. And by using this strategy, we were able
So next, let's move to the task 2. So the question given is calculate the area bounded by the curve y equal to negative 3x tangent times 2 minus 3 over cube root of x. The x-axis given is x, which is the lower boundary is negative 10, and the upper boundary here is negative 2. And by using trapezium rule with 4 and 8 subinterval, leave the final answers correct to 7 significant figures. Okay. So for the task 2, we can use Excel to calculate the approximate definite integral using trapezoid method. So in this method, we are using trapezoid instead of rectangles to approximate the area under the curve. So firstly, we will set up the column with the information we needed. So as you can see here, the first column here, we put it as a A, which is represent as a lower boundary, and B is the upper boundary. And we, based on the question given, the lower boundary is negative 10 and upper boundary is negative 4. And the N here is the subinterval that we're gonna use. So as for the first sheet, we are going to use the subinterval of 4. And in the A1 column here, we will set it as a value of x, which is that we will be used to evaluate the function. Okay. So for the task 2, we can use Excel to calculate the approximate.
So for B1, we set as the function given, which is y equals to the function given. So next is coefficient here is referring to the coefficient used in trapezoid rule. So we apply the first and last row as 1 and along the middle is 2 according to the trapezoid formula. So the last 4 column, coefficient times with function is where columns 2 times with column 3. This is where we calculated the value of sum of function with coefficient as stated in the trapezoid formula. Finally, we calculated the approximate area by multiplying the value of sum just now with the half and value of delta x, which is width. Thus, we will see the approximate value area under the curve for subinterval 4. Then, we will repeat the same step or copy everything to second sheet by using a subinterval or trapezoids. Finally, we will see both of the values subinterval 4 and 8 approximately with the value we substitute in the Desmos graph, which is So for B1, we set as the function given, which is equals to the function given. So next is coefficient here is referring to the coefficient used in trapezoid rule. So we apply the first and last row as 1 and along the middle is 2 according to the trapezoid formula. So the last 4 column, coefficient times with function is where columns 2 times with column 3. This is where we calculated the value of sum of function with coefficient as stated in the trapezoid formula. Finally, we calculated the approximate area by multiplying the value of sum just now with the half